Hi, and welcome again to my Physics Online video lecture series. Today's video we're going to be looking at the range equation. So this is a video that continues with our discussion of 2D kinematics. And what we're considering in today's video is just a basic equation that you can use if you have a projectile which has constant acceleration and which has essentially the same starting and ending height above the ground. So it's a symmetric projectile motion. Basically that means that this equation that we're getting for today assumes that the object starts here and is projected and then lands back at the same height that it began. So range equation will work here. So range equation should work for this. And then that could be contrasted with something like this, where maybe there's an object that's being shot off from a height and then landing somewhere lower. So if the object is being projected like this, then the range equation will not work. Similarly, if the object is being projected up onto a height that is higher than what it started for, this won't work either. So range equation doesn't work. This is the range equation is not valid here. Or maybe not valid for finding the actual solution to the problems. So that's something that's very important to keep in mind in what I'm putting here from the get-go. A lot of people I've seen in class will try to use the range equation in this situation or this situation, and it can't really be used to solve for these situations. It is used to solve for this situation only. So how does the range equation work? The range equation basically is there to solve for the horizontal distance covered when shooting or projecting an object across flat ground, or catching it at the same height that it was released from. So if the object travels like this, then we have a range which is the distance traveled horizontally by the object from start to finish. So this is like start, and this is like finish. And this range, r equals delta x, is v x initial times time. Now, how do we solve for time? Well, basically we need to use the vertical component. So let's say that the projectile is sort of projected initially with some speed v at some angle phi with respect to the horizontal direction. It follows that vxi would be v, let's call this v initial, be v initial times cosine phi, and vy initial would be v initial times sine of phi. Now, using what we know about kinematics, we know that when the object attains its maximum height, the y component of velocity will be 0. But we also know that vy is equal to vy initial minus g times time. Alright, so putting all these things together, what we can get is a value for the time. Time must be vy initial divided by g, which in turn is vi times sine phi divided by g. So if we plug that in for time into the range equation, it follows that the range is given by VI cosine phi times VI sine phi all over G. Now we can invoke a trig identity. With one little caveat here, got to be careful, because I've used t for two things here. This right here is t to get to the top, and this is the total time. So if we're calling this the time to get to the top, then this right here actually is 2 times the time to get to the top, because it has to go up and come back down. Effectively, what that means is that we include a factor of 2 down here. Now, we use a trigonometry identity. What that trigonometry identity says is that 2 cosine phi sine phi should be equal to sine of 2 phi. So this is equal to V initial squared sine of 2 phi divided by G. Alright, so again, the range equation says that R is V initial squared sine of 2 times the initial angle at which the thing was projected divided by the free fall acceleration. Okay, this predicts for us how far an object will travel horizontally before it re-impacts on the ground. And that's it. That's what this equation does. Now, there is one conceptual thing we can do with it, which is to ask for what angle is the maximum horizontal distance achieved, assuming that the thing is being projected across horizontal ground, level ground. And the answer is that to maximize this, our maximum happens when V initial squared over G times sine of 2 phi is simply V initial squared over G. In other words, the maximum value of sine 2 phi maximum is equal to 1. And sine of 2 phi equals 1 when phi is equal to 45 degrees. It also technically would work for phi is 135 degrees. It'd just be that it's going in the opposite direction. So phi equals 135 degrees will also work here, as it turns out. Now, as it further turns out, this would give a negative value for the range, and so that is essentially equivalent to shooting one way or shooting the other way. Okay, let's do a quick example. All right, for our example, a cannon shoots a ball with an initial velocity of 264 meters per second with an angle of elevation 27 degrees. We want to know how far away the ball lands, assuming that the ground is treatable as flat and there's no air resistance. So we basically just use the range equation to get the answer. This how far away question is R. This right here is your V initial. This is your phi. And of course G is 9.8 meters per second squared. So R should look like V initial squared sine of 2 phi initial, or initial angle, G. So that is 264 meters per second, quantity squared, times the sine of 2 times 27 degrees. Make sure your calculator's in degree mode, of course. Divided by 9.8 meters per second squared. If we plug all that into our calculator, we get 5,753.5967 meters. We should probably round that to about 2 significant figures, given what we've chosen for G and what we've chosen for the angle. So round it to 2 significant figures. That's about 5,800 meters. All right, well, that's it for today's video. It is one of my shorter videos, but hopefully you've learned something from it, and thanks for watching. See you in the next video.